Welcome to the lecture on Introduction to Turbulence in Fluid Flow. So, we had the discussion about the governing equations for fluid flow, and when we talk about fluid flow, then in that case the flow may be laminar or may be turbulent, and we need to know things about turbulence, because most of the flows which we will deal, they will be of the turbulent nature. So, what are the essential terminologies and what turbulence means, what needs to be modeled while we are solving for the fluid flow problems in these tundish or in any vessel where the flow is turbulent. So, we will have some introduction about these terms, and we will know more about these turbulent flows modeling and the associated terms in our coming lectures. So, as you know that when we talk about the flow, then we basically decide by the Reynolds number whether the flow is laminar or turbulent. So, if the Reynolds number value, so that will be less, in that case it will be laminar, and if it is more, so at low Reynolds number flow will be laminar, and at high Reynolds number flow is observed to be turbulent. So, your Reynolds number for that, the expression will be Re equal to U L upon eta. So, you will have these characteristic velocity, characteristic length, and then the kinematic viscosity of the fluid in the denominator. So, that way you get these value of the Reynolds number, and then you differentiate whether the flow is laminar or the turbulent. So, certainly there will be also a situation when there will be transition from laminar to turbulence. So, that will be another thing which will be there. Now, Reynolds number of flow gives a measure of relative importance of inertia forces and viscous forces. So, as we know that Reynolds number is inertia force upon viscous force. So, if it is of smaller value, it means viscous forces are more dominant, and if the Reynolds number is very high, it means inertia forces are dominating. So, so that way whenever you will have those regions. So, depending upon the Reynolds number, we can say that which kind of forces are dominating, which is more prominent. Now, what happens that when we talk about the turbulence, so basically you will have fluctuations. Now, the difference between the laminar and turbulence is that in case of turbulence, what is happening, that those length scales become quite large, over which the mixing takes place. There will be fluctuations in the variable values like velocity, pressure or so. So, they will be fluctuating over the mean values. So, in fact, the fluctuation in the velocities will give rise to another additional stress, which we have seen that certainly that in earlier lectures we have seen that you have stress terms, and they are expressed in terms of velocity gradient term and all that. Now, in this case your fluctuation terms which you are encountering because of the turbulence, now they lead to extra or additional stress terms. So, they are known as Reynolds stress terms. So, they need to be modeled, they need to be taken into account. So, these things are important when we talk about the Reynolds number of flow, and as you see that you will have depending upon the number, you see that which force is important. Now, you know that you have a critical Reynolds number. So, below that it is laminar, and above that it is turbulent. So, when the value of the critical Reynolds number, value of the Reynolds number is below the critical Reynolds number, then the flow is laminar, and in that you have the adjacent the flow is smooth and adjacent layers of fluid slide past each other. So, that is what the traits of the laminar flow is, that your flow will be smooth and your adjacent layers will be sliding one above other. So, they will not be mixing across in the cross devised manner. So, they will be going, and then there will maybe some diffusion of the atoms will be taking place from the bottom layer to the top layer or top layer to the bottom layer, like that. So, that is what is happening in the case of the laminar flow, and in that case, if your applied boundary conditions are not changing with the time, then we call it the flow is steady, and the regime will be the laminar flow. Now, there is another regime that is your turbulent regime, and that is that you are encountering when you see that the Reynolds number value is going beyond a certain value, that is critical value, and in that basically there will be complicated series of events will be taking place. So, there will be radical change of the flow. So, you will have a lot of events taking place in that, and basically what happens that finally the behavior of the fluid that becomes random and chaotic. In this, it is in a very defined manner, the flow is flowing one above other flow is there. But in that case, it becomes very chaotic as well as random. There will be mixing, there will be eddies, smaller eddies will be there, larger eddies will be there. So, all the diffusion which is taking place, they will be at higher scales. So, because there may be diffusion or the mixing over the larger bulk. So, maybe if you have 1, 2, 3 or 4 and 5 layers, so maybe 1 and 5 layer may mix because of these turbulence. So, that is the basic difference. So, your behavior that is what it there are radical changes in the flow character. Your flow becomes random and chaotic, and that regime which you get, that is known as the turbulent flow. So, if you try to see the the velocity measurement in case of a turbulent flow, then the velocity measurement basically will be like you will have the time here, and if your velocity is here. So, what happens that your flow will be, so suppose this is u. So, your actual flow will be like, it will be going like this. So, it will be going, it will be fluctuating. So, in normal case you can assume it to be fluctuating over a certain mean value. So, that is so you will have a steady state mean value, that is u. So, you will your this value, that is will be in the case of turbulent flow, you will have a mean value and you have the fluctuating component. So, basically at any time u t will be u. So, that will be your mean component, and then you will have a fluctuating component. So, that is u prime t. So, that way the turbulence in case of turbulence, the flow is basically characterized, and you will have this for all the properties like either be it u or be it v or w or p. So, for all that you will have a mean value and a fluctuating component. This component basically that component is this component above the mean, that is the fluctuating component, that is u prime t. So, that way your so you will have many statistical descriptors will be used while we try to know more about the the turbulent flow. Now, while in normal case when your you will have two space dimensions for the velocity of pressure. Now, turbulent fluctuations, when there are, they will have the three dimensional character. So, that is the trait about the turbulence. Now, in this case what happens that you have the presence of eddies, and if you look at the turbulent flow. So, in that flow structures you will have the presence of eddies. So, these eddies may be of smaller dimension or the larger dimension, and they can be of size. So, they can maybe of a smaller size, intermediate size, or even the larger size, maybe to the extent of the length of the vessel or so. So, that way you will have the presence of eddies, and in that because of these eddies the point which are largely separated in the vessel, they also come in intimate contact because of the flow structures in the case of turbulent flow, and there will be very high value of diffusive transfer or I think transfer of mass, heat or momentum in the case of turbulence. So, that is the basically trait about the turbulent flow. So, you will have the production of or the genesis of very high value of the coefficient of diffusion when we talk about the turbulent flows. Now, the thing is that in this case you have the characteristic velocity and the characteristic length, and they have of the larger eddies are basically same of the for the larger eddies. Suppose the characteristic length, that is L will be same as the length scale L of the mean flow. So, similarly the velocity also characteristic velocity for the larger eddies will be same as that of the mean flow velocity u. So, that is normally there in the case of the turbulent flows. Now, when we talk about the other scales, other properties, suppose if you go for those when the turbulence is very small, suppose turbulent if you talk about the Reynolds number. Now, in the Reynolds number you have the ratio, that is inertia force by viscous force. So, when your inertia force and viscous force will be somewhat nearly equal, in that case Reynolds number is close to 1. So, that tells that your viscous force is quite high. So, it is something that is why it is close to about 1. Otherwise, when you go in the upstream, so that is your depending upon. So, if you take suppose the u L upon eta, if the u is 1 meter per second, L is 1 meter, and your eta in normal case becomes 10 raised to the power minus 6 or so. So, that in that also you see that the value of the Reynolds number becomes 10 raised to the power 6. So, that is how so that will be inertia dominated kind of flow. So, we will come to this further if you try to know about the turbulence. So, you will have the transition to turbulence, and in the case of different kind of flows you will have a Reynolds number which will say that here the transition takes place, and in the case of pipe flow transition you will have the category of flow without inflection point. So, basically there are two cases. There may be the presence of inflection point when you have the transition to turbulence, or you may have the case without the presence of these inflection points. So, that way you will have so that depends upon the different situations. Now, the viscous theory of hydrodynamic stability predicts that these flows are unconditionally stable to infinitesimally disturbances at all Reynolds number in case of pipe flow, And in the case of pipe flow, the transition to turbulence will be taking place between Reynolds number 2000 and 1 lakh. So, basically normally what we might have studied about the transitions in case of these pipe flows. Before that, when we were talking about the turbulence, so in that we talked about the smaller eddies and the larger eddies, and the larger eddies, basically they will be dominated by the inertia effects, and the viscous effects are negligible in that case. So, so normally the larger eddies which are there, so these are basically inviscid or effectively inviscid. So, basically if you look at the values u L upon eta, so in that case if you take u and L and what we saw, so if you are taking that length as a characteristic length and we are taking larger eddies into account, in that case though the Reynolds number becomes very high. So, inertia force is dominating. So, in that case your the flow is inviscid, viscous forces are negligible, their effect is negligible. So, that is why we take it as the inviscid. Now, in those cases your angular momentum is conserved, and that is why that leads to I mean during that vortex stretching, this angular momentum is said to be conserved. So, that will lead to the rotation rate to further increase, and the radius of the cross section will decrease. So, that way you will have that kind of flow structure which will be coming up in the case of the turbulence, and you will have the and also what happens that you will have the mean flow, you will have the larger eddies, you will have smaller eddies. So, they will be deriving the energy from the mean flow. So, that way, and also the turbulence is said to be self dissipating also. So, those terms we will be discussing later. Now, coming to the turbulence and the transition to the turbulence, if you look at. So, this we discussed that for the pipe flow that was the case where and for different kind of flows you will have the in different way you will have the transition taking place, as we were discussing that when we talk about the velocity profile that will be susceptible to the different kind of flows and will be creating the instability. So, the inflection point which we are discussing, that you will have when you may have the instability and the velocity profiles may be like, if your velocity profile goes like this. So, basically this is the point of inflection. So, and this is your y and this is your velocity. Similarly, when you have you can have the transition of the turbulence also, transition to turbulence even without the inflection point. So, your situation may go like this. So, that may be in this case you have this is your inviscid instability. So, in that case viscous effects are negligible, and this is your viscous instability. So, this is basically the velocity profile which you see. So, this is with the presence of inflection point, and this is without the presence of the inflection point. So, that is what is normally happening when we have the transitions to turbulence taking place. Now, that is basically for the different there may be different kind of flows. You have jet flow, you have also the so in that jet flow, and then you have the mixing, or you have the many cases. So mixing or flow behind the wake and all that. So in all those cases you will have you must have the idea about how the turbulence takes place, how there is how suppose in jet, so it will be moving, so it will be a moving fluid, and that will be interacting with the stationary fluid which is there. So accordingly you will have a deformation and all that. So this needs to be we expect that you have some understanding of these phenomena, and that will help you basically in understanding basically the terminologies which will be coming later related to the turbulence. Now coming to some descriptors of the turbulent flow. So when we as we discussed that in the case of turbulent flow, you have a mean component and one is your fluctuating component. So so what we do is normally the mean phi of the flow property. So you will have the flow property phi, and this will be defined as the mean phi plus phi prime t. So that way we define. So basically for the turbulent flow, for any property for turbulent flow, when we talk about any property phi at time t. So this phi at time t, so that will be defined as the mean value. So that is phi, and plus you will have the fluctuating component phi dash phi prime t. So that way your this is how the property will be there in the case of the turbulent flow. Now the thing is that for as far as this fluctuating part is there, so for this the if you take the time varying component and if you take its value, so basically its time mean will be 0 for the fluctuating component. So so you will have the other there are different ways to express this, and one is the time average or mean. So for any property phi, the mean phi, that mean will be denoted as, so that will be basically so that is shown here. So your this mean of the flow property is defined as we are taking 1 by delta t, and 0 to delta t you have phi t delta t. So that way we define the mean of the flow property, and then you have the fluctuating component also. So you may we should take that limit towards the infinity, but then you will have but you will have to take the delta t cautiously, because you have certainly a size of the, there is a limitation on the, that limitation is put by the size of the eddies. So that slowest variation will be because of the largest eddies. So accordingly you will have to take the delta t. Now if you take the time average value of the fluctuations, so by definition the time average value of the fluctuation will be taken as 0. So if you the fluctuation which we had seen in the first case, that you have the mean value and then fluctuation taking place. So basically it is assumed that the if you take the time average of this value, it will be coming to 0. So that is why you have a mean value and then you have the time average value. So we write normally when we do not take the t into every time for the notation. So we will be writing phi equal to mean phi plus phi prime. So that way we are writing these values. Now, apart from that you have other properties. So, other properties will be your now this fluctuation component of the suppose velocity we are taking into account. So, this fluctuation component will also be leading to the energy also. So, the total kinetic energy so these fluctuating parts which that give rise to the kinetic energy, they are the turbulent kinetic energy known as. So, you will have the turbulent kinetic energy. So, this turbulent kinetic energy per unit mass. So, this will be by the respective velocity fluctuations, and that will be equal to half of u prime square plus v prime square and plus so you will have a square and then w prime square. So, that way this term, because of this fluctuation part which is squared. So, that gives you basically the turbulent kinetic energy per unit mass, and this is basically to be taken into account, and when we deal with the turbulent flows modeling, in that case this will be used. Similarly, you have based on this you define the turbulence intensity. So, that is basically defined, and turbulence intensity will be the average RMS. So, it will be depending upon the RMS velocity. Now, before that we need to know what is the variance and RMS. So, first of all we are talking about the variance. So, the variance it will be defined as 1 by delta t and phi prime square dt. So, that is how the variance is calculated. So, you will have the fluctuation part, it is a square, and then we are dividing by delta t if you are integrating over delta t. So, this way we are getting the variance, and the RMS value of this fluctuating part. So, that phi RMS, that will be the square root of this. So, this is your square root, and basically what happens that before that we need to understand that the u prime square or v prime square or w prime square bar on all these components. So, they give rise to the some of the stress terms. So, so that is why and these are and these stresses which are because of these fluctuation components. So, we call it as Reynolds stresses, that is what we discussed. And then we defined this turbulent kinetic energy. So, that will be k equal to half of u prime square plus v prime square plus w prime square, and the turbulence intensity, that is the average RMS velocity divided by the reference mean flow. So, this will be average RMS velocity divided by reference mean flow. So, mean flow velocity. So, if you take reference mean flow velocity as u reference, so what you do is you can derive it through this k. So, that will be 2 by 3 of this k. So, T I will be 2 by 3 k, and it is half because you will have one velocity component. So, you will have 3 by 2. So, 2 by 3 you multiply, and so it will be velocity component, that is your RMS velocity, and then it will be divided by the u reference. So, this way you define these turbulence intensity, and this will be one of the parameters which will be used when we are going to give the boundary conditions in the case of the flow where the turbulence will be used. Apart from that, you have even the terms like the moment of these different fluctuating variables. So, that will lead to the terms like u prime v prime bar or v prime w prime bar, that leads to these stresses. So that those terms there will be the additional shear stresses, they will be coming up when we deal with turbulence. So when we go to deal with the Navier-Stokes for that Reynolds averaging, Navier-Stokes equations, where we take these turbulence flow into account, in that case we will see that these terms will also come into picture. That will be the extra Reynolds, that is shear stress, that will be coming up. So accordingly these terms need to be understood, and that we will see more of these terminologies in our coming lectures. Thank you very much.